Today we're talking about perpendicular bisectors and angle bisectors. So it's a very vocab intense chapter. So most of the math in this chapter is not hard. It's all the vocabulary and keeping everything straight. Okay? So the sheets, the foldables that I'm going to be giving you are things to review and help you out. I'll have some flashcards both in electronic form and also in paper form. So if you prefer a paper form of flashcards, I'll have those for you. We're going to work on, we have posters on the wall. All of these things are going to help us with all this vocabulary. The math isn't hard, just a lot of vocab. So we're suddenly throwing a language lesson in at you, or an English lesson. Okay, so that's what your foldable looks like. Again, we're working on the left-hand side first. And we want to talk about a perpendicular bisector. So when you hear the words perpendicular bisector, what does perpendicular mean? Yeah, it's like a T. Upside down T is how we kind of show it, right? Or actually the right side. Yeah, upside down T is how we show it, right? And perpendicular means that it forms what kind of angles? Right angles, okay? 90-degree angles. Bisector, what does the word bisector mean? Cuts it in half, splits something exactly into two equal parts. So if it's a segment, we now have two congruent segments. If it's an angle, we now have two congruent angles that are half as big as the original ones. Okay? So let's look at what happens when we find or create a perpendicular bisector. So this is just a little GeoGebra demonstration, a little applet. And it says, hey, if you want to create a perpendicular bisector or show that P, line P, is a perpendicular bisector, that means that it has to, first of all, split segment AB into two congruent parts. And also, it needs to make two congruent angles. And those congruent angles will have a measure of how much? Take a straight angle and we break it into two congruent angles. 180 divided by 2 is 90. So these will be perpendicular. Okay? So we need to come up with a definition of a perpendicular bisector. And it's going to say something like this. A perpendicular bisector of a line segment in our top left box. Perpendicular bisector of a line segment is a line that is perpendicular to the segment at its midpoint. Keyword there, midpoint. So this line, CP, is perpendicular to segment AB at its midpoint. Midpoint is point P. So point P bisected it, cut it into two equal parts. We're looking for these marks, these symbols, and then we're also looking for a right angle. Okay, that means it's perpendicular. Questions so far? Easy enough, right? Okay, so let's talk about the perpendicular bisector theorem then. So when we bring this little applet up, it's going to tell us that if we bring point C down, and you can't really see that. Let me change the settings here. Options, font, size. All right, everybody see that better? Okay, we have 7.06 and 7.06. As I move point C, 3.91, right? 3.68. 3.5 on both sides. 3.47, and so on. Okay? What do you notice about those distance between C and the endpoints? They stay the same. They're going to be congruent, okay? 6.94, 6.94, okay? So those are congruent. So when we look at the locus of all points that are equidistant from point A and B, we see that it's all of these guys along this trace line. Let's check out the midpoint. Guess what? It went through the midpoint, didn't it? And we have a right angle down here. So what is this line? This line is the perpendicular bisector, right? Okay. And is equidistant. Anybody who's on this line is equidistant from the endpoints. Okay. So let's go back to our little presentation here. So this is the perpendicular bisector theorem. Second block. In a plane, if a point lies on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. If C lies on the perpendicular bisector of segment AB, then the distance between A and C has to be the same as the distance between C and B. So far, so good? What does the word equidistant mean? What does it sound like? Equal distance, right? So equidistant means that they have the same measure. Okay? So far, so good? Questions on this? All right, so we'll keep it moving. So, converse of the perpendicular bisector theorem. What did the converse do? We had a conditional statement. It did what? Yeah, it flipped them. It switched them. Okay? Change the order. Okay? So, if something is equidistant from the endpoints of the segment, then it has to be on the perpendicular bisector, right? We just switch our if and then around. So that's what's going on here. Let's show it. Okay. So here's our C that happens to be on the perpendicular bisector, and guess what? It happens to be equidistant. Doesn't matter what I do, it's equidistant from the endpoints. Okay? So we'll minimize this. And there's a little bit more writing to do. You can decide if you want to write the top or the bottom or something of your own that makes sense to you. Okay? We're in the converse of the perpendicular bisector portion of our notes. And it says, in a plane, if a point is equidistant from the endpoints of a segment, then it has to lie on the perpendicular bisector of the segment. So D is an equal distance from A as it is from B, and that's going to force it to lie on line CP, which is the perpendicular bisector. If we extend that line out, D will have to be a part of that line. Has to be on it. Since you have the picture there, you could simply say if DA equals DB, then point D lies on the perpendicular bisector of segment AB. Questions on this one? Not too hard, right? Nothing too earth-shattering here. It looks right. It makes sense. It's just a lot of vocabulary. Perpendicular, bisector, midpoint, equidistant, right? All this vocab. All right, so let's look at the next piece of it. So this is how easy these problems are going to be. A lot of vocab, but the math is easy. First example, we want to find the distance between C and D. So you have to look at the symbols of this. We see a perpendicular mark, right? And we see two congruent segments, don't we? So what is line BD? The perpendicular bisector, right? So since this is the perpendicular bisector, then the distance between A and D has to be, yeah, the same as the distance between D and C. So what's the distance between C and D? 27. That's how easy some of the math is going to be. Okay, but you have to recognize those properties. Okay? This is 27 because these two have to be congruent. Okay? All right, next example. Now we want to find the distance between P and R. Jaden? I love it. Since these two distances are the same, that means that it has to be on the perpendicular bisector, right? Which forces these two to be equal. So QR is 5. Have we answered our question? Not quite, right? What do they want? The distance between P and R, so they have to make it a little bit tougher, right? It's 10. So watch to make sure that you've answered the question. Okay, that's how these kinds of problems can be on the ACT and have a lot of people miss them. Because we can realize, oh, this has got to be 5, and 5 will be one of the answers or one of the responses that are listed. But then the distance between these two, we haven't actually answered the full question. Sadie. Okay, so when we notice that we have an isosceles triangle here, basically, that S is equal distance from P and R, then we know by the converse of the perpendicular bisector theorem that this has to be a perpendicular bisector. Okay, so they gave us the perpendicular mark, but that meant that this Q has to be the midpoint of that segment. And so once we recognize that, this will be 5 and this will be 5. And then we have to watch and make sure that we're answering our question. Okay? Other questions on this one? Make sense? Not hard, right? Okay, just watch your directions. All right, here's our next example, next box. It's going to ask us to find the distance between G and H. Now they throw some algebra to us, right? But we've done things that are much harder than this. So we want the distance between G and H. So we have to look and say, what do we see in our drawing? I see a right angle, right? And I see that a segment's been bisected. So this is a perpendicular bisector, right? So what do we know? What do you think, Chris? What do we know? So what are our two, what's it going to say? What's our equation going to say? Since we know that this is on the perpendicular bisector, those two have to be congruent. So what do you want to, how do you want to write your equation? (3x minus 8 equals 2x), or we could have said 2x equals 3x minus 8, right? Doesn't matter which order we write them in. Okay? Now we've got variables on both sides, but numbers on one side. So what are we going to do? Yeah, let's subtract that 3x to take it to the opposite side. So that's gone, and we get a negative 8 is equal to a negative x. So what's x? Positive 8. Are we done? Ask yourself that question every time. Are we done? No, we're not done. So what do we have to do? We're trying to find the distance between G and H. We have to plug it in. Which one's easier to plug it into? The top one. They're equal, aren't they? So don't throw yourself into more mental cycles than you need to. Since x is 8, we could take 3 times 8 and subtract 8, or we can just simply take 2 times 8 and get the same answer. So what's our answer? 16. so don't stop short. Make sure you're answering the question. Math is easy on these. The most difficult part is making sure you answer the question. Okay? So far, so good? All right. So 2 years ago, around Thanksgiving time, I went to visit my sister out in Colorado, in Steamboat Springs, Colorado. And we went on a hike and had dressed up in blues and grays and wanted to take a picture by Fish Creek Falls out near Colorado Springs. Or not Colorado Springs, but it's near Steamboat Springs. So this is the bridge that we stood on, and toward the back was a frozen waterfall that we had in the back of our picture. But being the geometry teacher that I am, I immediately saw that this was something that relates to math. What can we conclude about this bridge? One more time. Yep, we've got a triangle, a triangular shaped bridge, don't we? Okay. And, or at least the supports on it are triangular shaped, right? And so we see, it's a little hard to see from the drawing, I didn't have very good choices here. But we see that we have a segment QR that's marked congruent to a segment RS, don't we? Okay, and this little support, this wire cable, was perpendicular to that span at point at R. So based on that, what is PR? What's its name? Perpendicular bisector. And now that we know it's a perpendicular bisector, what can we conclude? Yep, QR, segment QR, is going to be congruent to segment RS. Or the distance between Q and R is equal to the distance between R and S. Oops, not Q and R, my fault. P to Q. So yes, we knew these, okay, based on the fact that they were given. And we had a perpendicular mark, so we know that PQ is equal to PS, the distance between them, or segment PQ is congruent to segment PS. Okay? So if they had part of the bridge that was failing, this piece for example, and they measured it, it should be the same length as this piece. So they could replace them both. Make sense? All right, so here we go. Now we want to move on and talk about angle bisectors. Okay? Remind me, what did bisect mean? Cuts it in half, splits it in half, okay? So think about a piece of cake when you're thinking about an angle bisector. Okay, you got this piece of cake and you got two kids that want that piece of cake. Okay, we need to split it exactly down the middle to appease them both so that they're both happy and think that they've got the same size slice. Make sense? All right, so with the angle bisector theorem, let's look and see what happens with this guy. All right, so another little applet here. Watch what happens as I move JK around. So this JK is congruent to this portion from the angle to D, and from D to this other portion of the angle, that ray. So D is being traced, and notice that it's leaving this little batch of color, right? Okay, and all this while we've got the same lengths. So far so good? Okay, so the angle bisector is going to be equidistant from the rays, from the angles, right? From the rays that make the angle. Okay, so here we go. If a point lies on the bisector of an angle, and it's equidistant from the two sides of the angle. If a point lies on the bisector of an angle, it will be equidistant from the two sides of the angle. Okay, now let's pretend that we're in a city park, and the city park is a block wide and a block deep. Okay, and you're somewhere in that city park, and you need to get to the sidewalk quickly. In which direction are you going to go? South, if this is a map, right? You're going to go straight south. Why south? It's the closest. And should I go southeast? No, straight south, right? So you're making a perpendicular to that sidewalk. You want to find the shortest path, right? The shortest path is always a perpendicular to that. You know it intuitively, whether we ever talk about it geometrically or not. Does that make sense? Okay. So that's why these are right angles. Okay. The shortest distance between 2 points is a straight line that forms a 90-degree angle with that line. Does that make sense? Okay. So when you're looking at these things, you're looking for right angles and you're looking for angle bisectors. So far so good? Okay, so here we go. Converse of the angle bisector theorem, I'm going to keep going. Okay, I think you're getting it. I don't want to waste time. Does that make sense? But what this says is that if a point is on the inside of an angle and it's equidistant from the two sides of the angle, these two distances are equal, then that means that that angle has been bisected. Okay? Angle BAD will be congruent to angle DAC. If a point lies on the interior of an angle and is equidistant from the two sides of the angle, then it lies on the bisector of the angle. This ray that cuts it into two equal angles. So far so good? All right. So here's how we're going to apply it. Again, you got to look at the symbols and know your vocab. Okay? We want to find the measure of angle ABC. So what do we notice? We've got right angles, right? And we have what? Congruent sides, right? So since these two are congruent, that's going to make these two angles be congruent as well, isn't it? And yes, AB and BC will be congruent because these will be congruent triangles. Okay? So once we know that these two are congruent, if angle DBC is 56 degrees, what do we know about ABD? Also 56, angle bisector. And if we're trying to find angle ABC, what do we have to do? Add them. 56 and 56 is 112. Math is not hard. Okay? Just a lot of vocabulary, a lot of symbolism. Okay? So you focus on that vocab, you won't be lost. How about the distance between J and M? What are we going to do? Austin, what are we going to do? What do you think, Sadie? Set up an equation. What's your equation going to say? Because this is an angle bisector, and we see these right angles, that means that this side and this have to be equal. The distances between M and J have to be equal to the distance between M and L. And then the algebra is easy, right? How do we solve this, Hank? Subtract 2x from both sides. And then what? Divide by 2. Now that we know that x is 6, have we answered our question? No. So we're back to having to plug it back in. The distance between J and M is going to be 24. Yep. The other one would also be 24. Okay. Everybody good? Okay. Then parachutist lands at TD Ameritrade Park. Okay. So he drops down out of the sky, lands right here. And now they're done, and he needs to walk to the sideline, right? He wants to walk to one of the foul, either the first baseline or the third baseline to get off the field. Which way should he go? First or third? You may not be able to see it, but there's marks here. I think. First baseline? Perpendicular to the first baseline? Anybody who thinks it should be the third baseline? Why are they the same? Okay. Should be the same if it's the angle bisector, right? So it won't matter. If he lands happens to land on the angle bisector, then either one should be the same. Make sense? Okay. All right. So this is where it can get tough. Okay? It doesn't have to be tough, because you know this stuff. Just have to be reminded. Okay? We want to write an equation of the perpendicular bisector of a segment that has endpoints at 5, -1, and -11, 3. So those points have been graphed. I didn't, for some reason, didn't connect the dots. I apologize. So connect the dots. And we want to write an equation of the perpendicular bisector. So it can be any form. Where do we begin? We want the equation of a line as the perpendicular bisector of this line. Okay? So what's the first thing we need to know? What's half of it? Where's the midpoint? Okay? So we've got to find that middle point in order to help us find the equation. So what's the midpoint formula? Almost. That was slope. x1 plus x2 over 2 and y1 plus y2 over 2. It's a point. So we add them up, and we're averaging. We add them up and divide by 2. Add your x's divided by 2. Add your y's divided by 2. Write it as a point. Ordered pair. Okay? So if we add 5 plus a -11, and we divide that by 2, it's going to be a -6 divided by 2, which is -3. And if we add a -1 plus 3 divided by 2, it'll be a 2 divided by 2, which is 1. Okay? So we found our midpoint. Okay? So our midpoint is at -3, 1. Ta-da. Halfway there. To write an equation, we need a point, and we need slope. We found our point. Right? How do we find the slope? Yes, sir. Rise over run. Good. So how much are we on this particular line? How much are we rising? Here's 2 points on this line. How much are we rising? How much are we running? Are we going uphill or downhill? Downhill. So we fell 1, right? And we ran 4. So our slope of this line is a -1/4. That's for that line. Okay? We went down 1 over 4. But on this particular line, we don't want that slope. We want the perpendicular bisector to it, right? The bisector part comes from the midpoint. How do we find the perpendicular? Not double. How do we find the perpendicular to a line? Flip it and change the sign. Okay? Perpendiculars are negative reciprocals, right? We flip them and change the sign. I just happened to look for a place where they cross so these are all nice points. This one, this one, this one, right? Or I could have found the slope from this. I could have said slope is y2 minus y1, x2 minus x1, right? And I could have subtracted, okay, and reduced. So there's a couple ways. If it's graphed and you've done a nice job and you use a straight edge or your planner or something to make a nice straight line, then you'll be able to see places where it crosses and find the slope. So far, so good? All right, so we have a slope of the original line. What's the slope of our new line, our perpendicular bisector, going to be? This one's negative 4 over 1. The perpendicular is going to be, sorry, this one was negative 1 over 4. The perpendicular is going to be positive 4 over 1, right? Okay, so our slope of our line will be 4. We know our point is negative 3, 1. So how do we find the equation of a line? If we have a point and a slope. Not midpoint, but nope, not distance. Y equals mx plus b. That's the slope y-intercept, or point slope, which is y equals, we modified this a little bit, y equals our slope times x minus its coordinate plus the y coordinate. Change the sign of this guy, leave that one the same. You want to see it in slope y-intercept or point slope? Point slope is easier. We don't have to do any work with it. Okay? So we say y equals, what's our new slope? 4, right? Times x minus a minus 3. Do a minus minus 3 or change the sign of negative 3. We're going to get plus 3 and then plus 1. There's our equation. Okay. Find the midpoint. Find the slope. Flip the slope. Plug them into point slope. Or put your 1 in for the y, the slope in for the slope, 3 in, negative 3 in for the x, and solve for b. Okay, they both work. You have to solve it and then substitute it back in. Okay. All right, do you want to see another example of these, or are you okay? You're good? I know it's a lot of notes. Okay. So there's the assignment. It's straight from your green sheet. First part's easy, just this coordinate geometry that's tough.